energy. This is AP Bio Unit 3. So let's talk about metabolism. Metabolism is a chemical reaction that takes place in a living thing. Anything that is alive has to be able to use energy to break down molecules, bring together molecules, and this is going to create chemical reactions. So here I have these molecules, and I add energy to it. I can put them together. If I want to break these apart, I can take an enzyme, break it down, and pull it into all these individual pieces. But for me to put them together, they're going to require energy. We have a catabolic pathway. This is the release of energy by the breakdown of complex molecules into simpler ones. So a good example is digestion. We have these molecules, and I'm going to go and I'm going to break it down to individual pieces, and I'm going to release energy. So this could be a hamburger. You take a hamburger, you eat it, and as you eat it, you're going to have enzymes, you're going to have some type of response that is going to break down those hamburger bits into pieces that you can use, and it's going to produce an energy. Now, the response is going to be different. So for example, I eat a hamburger, the hamburger is not going to stay the same way throughout. So I'm going to be able to use certain parts, and other parts will be waste product that will be taken out. Anabolic are pieces that come back together. So you're going to bring in energy or consume energy to build a more complex molecule from simple ones. So an example would be protein production from exercising. I go and I have to take all these different pieces together, and I need to put them as one. So I need to add energy to that to make it all into one piece. I'm putting all of these little circles together. So an example of that would be eating. I want to eat and I want to make muscle. So I'm going to take all of these pieces, all of these individual parts. I have to add energy to it, and it's going to put all these pieces together. It's going to rearrange it. And then I can have muscle building or muscle production from these pieces plus energy. So energy can come in different forms. So let's talk about kinetic energy. Kinetic energy is going to be energy based on motion. So the person was standing up here, they jump as they are moving. This is going to be energy due to motion. They are going to have energy as they fall. Potential energy is going to be energy based on height. So up here I'm going to have height. The higher I am, the more kinetic energy I could get from that height. So I have the potential to have more energy from the height, the higher up I am. So this boy has more potential energy, but when the boy gets to this point, he has less potential energy because his height has changed. His kinetic energy could change. I have lower kinetic energy, and then I have higher because he's speeding up. As he comes down, I could have more kinetic energy here as he's about to hit the water. Chemical energy is going to be the energy found in bonds. So when you eat something like a pizza, you have a lot of chemical energy in all those bonds of food. And so that energy will be released when those bonds are broken. So the first law of thermodynamics, this says that the energy of our universe is constant. This means that our energy is pretty much fixed. It cannot be created or destroyed. I cannot create energy. I cannot destroy energy. So the example I used is a piece of bread. I have a loaf of bread. And if I take this loaf of bread and I start pulling it apart and ripping it, I can still eat it. It's still bread. But there's going to come a point where all that bread could be breadcrumbs. And I really can't do it. And I can make those breadcrumbs even and make it into dust. And that's going to be a point where it's still bread, but the bread is so small that it's basically useless. Like it's energy, but the energy is so minute. Is kind of how that works. So think of bread, and I have all these. I can bring it down to dust. It's all the bread's still there. It's just so spread out. And energy does the same thing. I cannot create it. I cannot destroy it, but I can change its form. So the energy has a certain amount of energy available. It's fixed. And so the only way I can do is move it around. So our universe has a bunch of energy in it, and it is constant. And another example you could use is this. I go camping and I make a campfire and I add fire to it. These molecules that are here, the energy that is here, is going to be released in this energy here. So this fire is going to break this energy down, and I'm going to transfer it into heat. I'm going to transfer it into smoke. I'm going to transfer it into light. All this energy is going to leave, but all the energy that was stored inside the wood, stored inside the grass clippings, whatever this is, all this energy that is stored is going to be released, and then I'm going to have less energy on this side. So if I tried to burn the ash, tried to burn the smoke, and I'm not going to get as much energy out of it as I would with the campfire. The second law of thermodynamics is also called the law of chaos. And if you just remember that, that kind of helps you with this law. This says that in every energy transfer, energy is broken into smaller units of energy. Let's go back to that bread example. So I have that loaf of bread. I have all of its bread, but I can get it down to where finally I'm at bread dust. So I can take that big piece and eventually bring it down to where it's almost nothing. It looks like nothing, but it's there in just a small amount. Energy cannot be recycled, and all living things must have a constant inflow of energy. For a living organism to stay alive, they have to be bringing energy in. They have to be bringing in a food source. They're either making their own food or ingesting. They have to have heat. They have to have all of these things to make sure that the energy coming in is keeping that organism going, the energy it needs to function. So I go back to this, okay, I have my fire, I have my ash, I have my smoke, okay. This has gotten a lot smaller, and I have put out heat, I put out light energy, smoke. This has gotten a lot smaller. My units of energy have shrunk. So let's talk about entropy. Entropy is the measure of molecular disorder or randomness. And this is the law of entropy, is also this part of that second law, the law of chaos. This is saying that when entropy is increased, disorder increases. So here I have an ice cube. This ice cube is very structured. All my molecules are real nice and tight together. But as my molecules become more random, more disordered, I start going into this liquid form. If I have a ink droplet, I put it in this water, this is going to just naturally start to spread out. I'm going to become more random. I'm going to create more disorder. This is too concentrated. This is too orderly. So it's going to spread out, and I'm going to create more randomness, more disorder. I have a room, and if you guys have ever lived in a bedroom, you know that it never stays as clean as it is when you've picked it up. It is very easy for it to go and to start to look like this. Something gets dropped, you have dust start to form, you have things on the carpet. It is very easy for it to go from a ordered to a disordered very easily. Like, it takes hardly any effort at all for your room to become messy. But to go from this back to this takes a lot of work. It takes a lot of energy to go from an disordered to an ordered. So we call this the law of chaos. It's easier for things to develop and break down and fall apart and become more random than it is for them to come together. So the second law of thermodynamics, the law of entropy, means it's spontaneous. I can go from high randomness, high entropy, high disorder, and if I become closer together, more ordered, less random, okay, my entropy is going to decrease as I become more ordered. The universe wants a high entropy, what we call an entropy tax. They want to have randomness, disorder is what the universe requires. So let's look at this. I have a bear and the bear's eating a fish. Okay, chemical energy is going to come from the food that the bear eats. These molecules are now going to come into the bear and become part of the bear. So this is the first law of thermodynamics. So I'm going to take this energy and the energy is going to be moved into the bear. The bear cannot create energy from the fish. It has to come from the fish. The second law of thermodynamics is the law of entropy, the law of chaos, that in order for energy to be available, it has to be broken down into smaller units. So the bear is very structured, it's very organized, and the only way that this bear can stay structured and organized is to pay that entropy tax, pay that chaos tax of creating more disorder in our universe. And the way the bear can create more disorder in our universe is to release energy as kinetic energy. It's going to release carbon dioxide. It's going to release water. Its body is going to release heat. So this fish that was very structured, very organized, is now going to get broken down into smaller and smaller pieces. So eventually everything will be broken down into this, and technically our universe at some point will have energy in amounts that aren't usable, but they're all there someplace somewhere. So we call this free energy, and it's a system's energy that can perform work when temperature in a system is uniform. So free energy, we call it a delta. Delta means a change, and we call it Gibbs. There is a scientist named Gibbs that came up with this idea. So we call it delta G or delta Gibbs. This is going to be a change in free energy. This H is total energy, and so this is the change in total energy. This is absolute temperature, which has to be in kelvins, and this is a change in entropy. S is entropy. This is the change in chaos. You will not be required to solve for this problem, but I'm letting you kind of know that if I have an increase in total energy, a decrease in entropy, that's going to change my delta G. So a change in total energy, a change in entropy can change my delta G. So let's look back at my ice cube. I have my ice cube, remember, it's very organized, very structured. It's going to have a very low entropy because I'm very organized. So I take that, I melt, so I'm going to become less organized, I'm going to become more random. I have my ink droplet. My ink droplet is going to spread out. I'm going to become more random. I have my room. I live in my room for a couple days, and then randomly I'm going to have stuff going all over the place. So I'm going from a low entropy to a high entropy. I'm going from low chaos to high chaos. I'm going from a low randomness to a high randomness. So we say this is going to be a negative delta G. This is going to be a negative delta Gibbs. This is going to be a spontaneous reaction. This means I'm going to have a negative value. So if you look back at that number, I'm either going to have a massive change in entropy, or I'm going to have a big change in total energy. And if I get a negative number from that, that's going to mean it's going to be a spontaneous reaction. If I have a positive number, a positive change in Gibbs, a positive delta G, this will not be spontaneous. This means that I would be going from this messy room to this cleaned room. I'd be going from this spread out dye to it all clumped up in the middle. I would be going from water going back to ice. This would not be a spontaneous reaction, okay? So we say exergonic reaction, this is energy that is released, it's going to be spontaneous, and it's going to release that free energy into the system. So I'm going to have a delta G, okay, and then I'm going to have my little alligator mouth saying that this is going to be greater than delta G. So when we look at this, I look at my graph. I have Gibbs free energy, I have time, I have my reactants, this is what's going into the system. Here's my products, this is what's coming out. And I tell my students, think of this like a slide, okay? I come in and I have to go up this little hump to get to the top of the slide. And then I'm going to go down. I'm going to have more energy released here than if my slide started here and I had to go all the way up and then I slid right here. So this is going to be more fun. I'm going to have more time to release energy as I go down to make my products. And another thing I'll say too, if my reactants are higher than my products, it's going to be exergonic. Energy is going to come out of the reaction. So the example of that would be gasoline in a piston, in an engine. I'm going to ignite it. It's just naturally going to produce pressure. It's going to produce gas. It's going to produce heat, light. I'm paying my entropy tax to the universe by going from very, very structured to very scattered, very random, releasing and breaking this energy down into smaller parts. If I'm eating food, this is going to be an exergonic reaction. I'm going to take the food, I'm going to eat it, I'm going to produce heat. I'm taking this and breaking it down into smaller and smaller pieces. I'm going to turn it into carbon dioxide through cellular respiration. So this would be an exergonic reaction. An endergonic reaction is going to need energy to proceed. Ender means inside. So it's going to have to absorb free energy. So it's going to require energy from a system. So an example of that would be something that is not spontaneous. So it's not going to be spontaneous. Here you can see my reactants are down here. My products are up here. This is, if I did this as a slide, this would not be a fun slide, right? This would be a very short slide. I have to crawl up all this way to get up here to this and then come down like this. So if you think of it like that, this is not going to be a energy that is going to be naturally, it's going to energy that has to go into it for you to be able to get up here at the top. So my reactants are below my products. That's also an endergonic reaction. So examples of this would be photosynthesis. For photosynthesis to start, I have to bring sunlight in. I have to bring this photon energy into the plant in order for photosynthesis to start. So here are my two. This is an exergonic. Energy is going to be released. It's spontaneous. Endergonic, energy is going in. It is not spontaneous. And side by side, you can see now my reactants are up here. My reactants are down here. My products are here. My products are here. And if you just remember the slide scenario, this is going to be a more fun slide. I'm going to be able to go all the way down. And I have to put very little energy into this point to get there. So this would be an exergonic reaction. Energy is going to be released. As I slide, it's going to be easier to release that energy. Here, my reactants are below my product, so I have to hike all the way up the slide, get up here, and slide. This is not going to be a very fun slide. I have to put more energy into it than is released. And so this is an endergonic reaction. So the breakdown of glucose, I take oxygen, and I could break it down into energy. I could break it down into carbon dioxide and water. This is fulfilling my second law of thermodynamics, my law of entropy. Okay, and this is going to be an exergonic reaction. Energy will be released from this reaction. And then I'm also paying my entropy tax. I'm breaking down this more complex molecule into something more complex as it goes. We can also do what's called energy coupling. This is the use of exergonic reaction to drive an endergonic reaction. So I'm using an action that is spontaneous to make an action that needs energy for it to be able to work. So here's an example. I have ATP, and ATP is going to pull off one of these phosphates. and one of these phosphates is going to leave, and then I'm going to have ADP and one inorganic phosphate. That PI, that's I is inorganic phosphate. And this energy is going to be enough to put something together. So I have a monomer. Remember, a monomer could be glucose, it could be amino acids, it's one little piece of one of those macromolecules. A monomer is going to get put together, and I'm going to start chaining these monomers with this energy that has been released. So this energy is enough to drive these monomers to start to attach. So energy coupling is being able to take this energy to do a task, to do work. So ATP is the primary source for energy coupling. The exergonic release of this phosphate, this one right here, is going to be used to do the endergonic work of the cell. So these bonds are really high energy because look at all these O's. Remember, all those O's, super electronegative. They do not like being by each other. They want to leave. And this one is going to very easily pop off when it gets the chance. And as it does, it's going to break this bond and it's going to release energy. And this phosphate is going to be enough to cause a endergonic action or endergonic work to be a process inside that cell. Enzymes, remember, those are proteins. They're made of amino acids. They're folded very specifically. So these enzymes will help to speed up a metabolic reaction by lowering the activation energy. So you can have enzymes be catalysts where they're breaking stuff apart. You can have enzymes be anabolic where they're putting pieces together. And this can be enough to cause this change in metabolic reactions because of these enzymes and the energy that they're able to use. So catabolic, I take my pieces, I put them inside my enzyme, my substrates come into the active site, they're going to be activated, the substrate's going to bind it, pull, break those bonds, and I'm going to have products get released. Anabolic, I'm going to have the pieces come in, I'm going to have a bond form, and then my new product will be these two pieces together. So activation energy is how much energy do I need to cause this reaction to happen. So here you can see my reaction from here to here, okay, or I should say from here to here is not as much, okay? If I'm going from here to here, I need all this energy to get from this part all the way up here. I don't need as much right here. I like to think of activation energy and enzymes kind of like somebody behind you on a slide. Like you go up to the very top of a slide and you sit there for a second and you kind of lean forward. You have to put a little bit of energy yourself, scooting yourself up to allow that to happen. But if you had somebody behind you that was able to help push you, you have to use a lot less energy to get yourself to go down the slide. Same thing if you're on a swing. I can swing my legs, but I can get a lot higher, a lot faster if I have someone behind helping me push. And activation energy is allowing that extra push or that extra nudge to get energy to be released a little quicker. So enzymes are able to affect that. So let's look at this. I have this purple line. Okay, this is what we saw on that last slide. But this right here now is my enzyme. Look at how much lower, how much less energy I need to be able to make this reaction happen with an enzyme. So without that, I have to come up here, I have to get all this energy without that enzyme. But if I'm able to get that enzyme, that extra person behind me to push, I can use a lot less energy myself to get down that slide or to go up on that swing. So this is kind of what enzymes help do. They lower the activation energy. They're lowering this hill that I have to climb to be able to go down that slide. All right, that's going to be enzymes, activation energy, free energy, delta Gibbs. If you guys have any questions, let me know. We'll talk to you later.